Morning, everybody. Yeah, online. Oh, good. Morning, everybody. My name is Cristian Antonio. I work at Pawsey as a supercomputing application specialist. That means I help researchers in various ways to run their workloads on the supercomputer, from optimizing their codes to working with them to find the exact configuration for them to run their programs on the supercomputer, understanding their needs in terms of compute and storage, etc. I also deliver training like today. I will walk you through a few modules that are meant to introduce you to the basic concept of supercomputing and how you can use supercomputers to run your workloads. In particular, this session is quite an introductory one, but will give you a good head start in terms of using the supercomputer to complete successfully your internship here at Pawsey. A few an overview of what we're going through today. So we had around 11 modules. That's quite a lot. Probably we won't be able to go in depth through all of them. I'll make sure to cover the most important concept. The first half, I think, is the one that actually all of them are important. We will see which one to skim over and which one to cover in depth. But all these topics are needed, or these items are needed that needs to be covered in a way for you to use a supercomputer. It's a quite complex environment. There are many concepts and many protocols and many things to keep in mind when using a supercomputer. And today, over 6 hours, we are going through these modules for you to learn how to interact with a supercomputer. I will be presenting module 1, 2, 5, and 6. 7 and 11, then Chris Harris in the back of the room will be presenting the other half. So we'll take turns to present. Okay. Let's get it started. The first part is a supercomputing introduction, an overview of essentially supercomputing. So in this first part, we'll take a look how we can describe the performance of a supercomputer, or in general performance of a computer, and we'll see what components, logical and physical, make parts of constitutes a supercomputer and a supercomputing environment. The important part of a supercomputer is the interconnect, that is the connection. The links between the various nodes of a supercomputer, we'll see better later. But at the end of this module, we'll be able to list the various components of a supercomputer. Throughout the slides and presentation, the following ones, we will have a few signs on the slides. Each one has a specific meaning. We look out for definition of new concepts and warnings, especially, so things that you should be aware of, things you shouldn't be doing, that is bad practices. This is because a supercomputer, as you will see, is quite different from your own computer or your laptop. So there are a few things that differ significantly, and I will point them out, and there will be signs like this warning sign to point them out. We'll have also some hands-on coding or like demonstrations, a very simple example for you to get the feeling on how to use the supercomputer. We will have slides indicating where to get the examples and how to run them on the supercomputer. And this is just an introductory presentation, but we will have all the information covered here and much more are present on our supercomputing documentation. There will be links throughout the slides. So make sure to go and take a look at the documentation. There's plenty of information there for you to get started now, and then throughout your internship, you will have that information available to you. All right, so this is a cheap slide. So how many computations can you do in 1 second? So how many floating point operations? And usually I just give 1 second and change slide and try again. So it's of course, I'm not expecting you to do that all of that in 1 second because we are not meant to do that. We have computers to perform as many computations as possible in 1 second. And we define a flop, so floating point operation per second, as a unit of measure of a performance, computational capability of a computer, and importantly of a supercomputer. A supercomputer is nowadays usually in the petaflop scale. So that means that we are able to perform 10 to the 15th operations per second. That's a massive number that is also hard to imagine. There are supercomputers, however, that are also in the exascale era. So we have the new supercomputers in the United States can access to up to, the most recent one can access to 1.7 exaflops of compute power. Photonics is more modest in that terms. It's got only 43 petaflops, but actually Photonics, when it came out, was 15th and the top in the list of the top 500 most powerful supercomputer in the world, and it was also fourth in the most in the category of most energy efficient. So, and it's still the most computational public computational infrastructure in Australia. For comparison, the previous supercomputer we had, it was around 1 petaflop. So we have seen an increase of around more than 40 times in computational capacity with the upgrade. Now, let's see. This list is slightly outdated by a couple of days or a week now. So this is the list of the most powerful public research supercomputing infrastructure in the world. Most of them are in the United States. So we had the first one, supercomputer, is Frontier, as of 2 weeks ago. But now that has changed. We have a new supercomputer called El Capitan, which is able to reach 1.7 exaflop. Frontier went to the second place, still in the exascale, and with 1.1, 1.2 exaflop. Aurora is yet another supercomputer with around 600 petaflops, still in the United States. And Photonics nowadays, in particular the GPU partition, sits at 28 in the top. Well, as before the list got updated a few weeks ago, it was sitting at 28. Now I'm pretty sure it's got a bit lower than that. And this is because every year supercomputers get upgraded, new ones get installed, and there is an ever-growing need of more computational capacity. And that's why supercomputers get deployed almost not every year, but there will be almost every year a new release. And the list is updated every 6 months. So every 6 months there may be a change in which one is the in the classification of the various supercomputers in this list. If you're curious, there are a few links here. So the top 500 is the website where you can check which one are the top 500 most powerful supercomputer in the world. Photonics as reaches that its computational power and its capacity through mostly 90%, around 90%, it comes from GPUs, and that's how all now the top supercomputers in the world reach their computational capacity while keeping, while also increasing their computational the density, and keeping and managing to store actually that much computational power in a single white space, right? That's because a GPU, as we will see, I will discuss later, has much more computational power. It can reach a higher number of floating point operations per second than a CPU, and it does so using less energy per flops. So it consumes slightly more energy in total than a CPU, but when you average over a number of operations you can do per second, then it's more energy efficient. That's why GPUs are, yes? Yeah, well, the list includes public infrastructure in terms that things that are not things that are accessible to the to do public activity, but in public, not in terms of like government. But there are also Chris wants to, but it's not limited to public sector. So there are companies who have supercomputers in the list, but by public research, I mean there are maybe other most powerful supercomputers you don't know about because they are kept a secret. Yeah. Yes, we have also a microphone going around for questions. Yeah. Okay. At Pawsey, we support a wide range of research and research fields. We are very known for our support to astronomy, so we have a lot of astronomers working on our systems. We had a dedicated system named Caravarla, and before that we had a dedicated system named Galaxy to support exclusively radio astronomy research. But Pawsey then since then grew bigger as a center, and we are supporting a wide range of science research fields. And we now have projects in the energy sector, resources, agriculture, and health. We have a wide range of projects we support, and Cetonix, with its computational power, is able to allow this wide range of research happening on the supercomputer at the same time. So Pawsey at first was dedicated to supporting radio astronomy research, but then it grew into a national facility supporting all type of research. Very quickly, I want to illustrate the main components of a supercomputer in terms of hardware. So this is what actually is installed there physically in the white space. It's a complex system. We have various, okay, my pointer is here, you can see it. So we have various racks, which are modular components that are connected together to then form the whole supercomputer. On the top, you have the cooling system that is starts from the tops, but then it's also it feeds coolant it goes straight to the nodes through these very complex systems of pipes that you see on one side of the supercomputer. Well, it's actually covered, but you will see these coolant pipes going into the compute chassis here, and then the compute blades. Each compute blade contains, depending whether it's a CPU or a GPU blade, can contain 2 or 4 nodes, and the coolant system is meant to cool down at the node level. So it's a quite complex system that needs to cool down components that are densely packed. So there is a trend of packing as much compute as possible into each blade and have this blade as packed together as much as possible, because you want the compute power to grow, but you also want to the space it takes to install the system to be still reasonable, right? And that also increases the need of complex cooling systems. So the cooling system is a big part of, as you can see. As I was saying, we have racks. Then on one level down, we have compute chassis that contain around, I believe, the chassis there are 8 chassis here, so 4 one side, 4 on the other side, and then they contain compute blades, around 8 compute blades, and then each compute blade contains 2 or 4 nodes. So it's a highly dense packed architecture. And we also have, on this side, we have the nodes. On the other side, that is not illustrated here, we have switches. Switches that basically are used to connect, the switches and the interconnect that are used to connect these nodes together. On the high level, or a more abstract level, a supercomputer is made up of login nodes. So this is how you access the supercomputer. You don't have a keyboard or a mouse like you have on your laptop or your own computer. You access a supercomputer remotely to the command line and SSH protocol. We have special nodes or computers, we can say, that are dedicated to allow people connecting to them and then interacting with the supercomputer. The login node is essentially the interface to the supercomputer. The compute node is where the computation is, where your program is actually will be executed. So your experiments, your simulations, your data analysis will run on the compute nodes, not on the login nodes, which are separate. These are two separate sets of nodes. The scheduler is a piece of software that takes your job or your computation or or better, the instructions to execute your computation and schedule it on the supercomputer. That means it places it on the compute nodes for execution at a certain time, depending on the condition of the systems. So we won't be able to run your job straight away on the compute nodes because they might be busy. The resources you requested may not be available. So instead of executing the computation right there and then, the scheduler will take your instructions, will take your commands, and put them in a queue. And then we'll execute your computation when the resources are available. So there will be a waiting time, and the scheduler will execute your job, and all of the others that are submitted by other researchers according to scheduling policies that are made to maximize the use of the supercomputer. So the goal is to use the supercomputer in the most efficient way. We will see that when we cover the job scheduling module better. Another important piece of the supercomputer is the storage. So in the compute nodes, you read data, you do some computation, and then you write out data, usually. And to do so, you need storage attached to the compute nodes. The high-performance storage is actually, you can see it as another compute system that is made of software and hardware. So you have disks or SSDs that then are organized or are managed by a software which is called the file system. A supercomputer has a high-performance file system that is able to serve many users at the same time and allow the various many computational jobs to run at the same time. Data mover nodes are dedicated nodes to move data in and out of the supercomputer, because sometimes you will transfer a lot of data, like in the terabytes or even petabyte scale. You need dedicated computers to perform such operations. So compute nodes are similar in terms of performance to very high-end workstations. But as I said, they are stripped away of all the accessories you may find on your laptop or like home desktop, such as keyboard or keyboard screen. You don't have a screen. You don't have. What you have there is essentially the CPUs or a GPUs, the network card, memory, and all the things you need to perform a computations, but also to allow all of this to be densely packed, on a blade. You will see, you can actually see the examples right here. There is, I'm sure you see in the cabinet, illustrating an example of a compute blade. So what happens here is that compute nodes are connected together they have high performance CPUs and GPUs, and they're connected together to high performance networking. That is because these computational resources, these high-end workstations, are meant to work together to solve bigger problems. Usually you run on a supercomputer jobs computational workloads that require many more resources than a single compute node can provide. That's why many jobs on a supercomputer utilize a number of compute nodes to work together to solve bigger problems. And they can do that by being connected together through this interconnect. Photonics has a slingshot interconnect connecting the various nodes together. And as you can see in the picture here, it's a rather complex systems of cables that are, if unrolled, can be also quite very long, and a complex system of switches connecting the nodes in a rack together and the nodes across racks as well. You can use a supercomputer in different ways. So you can have a single job or a single computation that spans over many nodes, so a very big computational job that is probably orchestrated through a message passing interface or MPI protocol. Or you can have many single jobs packed together. You can have many replicas of the same job working on different data. Or so basically you can use a supercomputer to do more computations or to perform a single computation faster. The storage, that is what we call also file system, is to the user is seen as a file system just like you have on your laptop. The difference is that it's quite spacious. You will see Photonics has around 13 petabytes of storage available on the Scratch file system, and the same file system or storage is visible across compute nodes. So you don't have to worry about moving data across nodes or trying to synchronize the storage across nodes, because all nodes see the same file system. So you read each node can read the same file or the same directory structure. In nodes, on GPU nodes some nodes may also have local storage, so storage that is private to the node. It may be on Photonics, we are in the process of configuring the NVMe, so very fast local storage dedicated to GPU nodes so that you can feed data to the GPU nodes in a faster way. A file system, in that sense, might be slightly slower than a dedicated storage on the node, because the data will have to go through the network to reach the compute node. So a very big file system like Scratch is installed physically in a different cabinets than the compute nodes. And to reach the data, compute node has to request data through the network, and the network will deliver data to the computer. This is done transparently to you, but it adds some overhead and some lag, but also the file system can provide you huge bandwidth. A local node storage is faster, but provides you less capacity. Okay. This is a high-level overview of the whole infrastructure. So we have Photonics that is connected to the various other systems at Pawsey through a very fast network system. I was saying this should be more like 13 petabytes, but we have our 5 systems connected through Photonics through the network, and through the same network you can access other type of storage we make available. 5 systems are short-term storage to be used just to load and write data to execute a job, but we expect the data to be moved out when the computation is done or shortly after, because the space, while it's big, it's still limited because we have a large amount of users using the file system at the same time. But we provide also other solutions to store data for the lifetime of the project, and that is the Acacia object storage. We will discuss it later. All these systems are connected to the system through the same network, and we also have some dedicated systems for astronomy here. to summarize, what we have available on Cetonix are around 10 login nodes, which a few of them are now repurposed to run workflow engines such as Nextflow and other software that are used to orchestrate jobs and to run jobs over the long term in an automated way. But we have around 10 login nodes, 16 data mover nodes to move data around, and we have 192 GPU nodes and around 1,600 CPU nodes. The interesting part is that these 192 GPU nodes provide much more computational power than the CPU nodes, even though they are in a higher number. But because the GPUs pack way much more computational power than a CPU does, then you have much more. Using GPUs, this partition will give you access to a much more computational power if you're able to use a GPU in your workflow. A home file system, software file systems, crash file systems, they will have different purposes, and we will be explained the following modules. We have a few file systems, and then the object storage for long-term storage, as I explained. Any questions so far? Okay. You can always stop me if you have questions. What is interesting about a supercomputer is definitely, of course, the amount of compute you have available, but also how these high-end workstations are connected together. The reason to have them all packed in a single space, in a relatively small space, is to allow them to communicate efficiently in a fast way. In a very distributed environment, you might have that the distance between computers can play a big role in the way they communicate. So if you have a computer here in Australia, a computer in America, then they have to work together. They can, but there will be a huge lag in the communication. So the reason a supercomputer is because you have this locality of computation that allows you to perform distributed computation in a fast way. And we also do that by having a layout of the network such that in our case, every two nodes are not more distant than 3 hops. So you pick any 2 compute nodes in Cetonix, their distance in terms of network is no more than 3 hops through switches or routers. In this way, we reduce the latency and the computation can proceed fast. This is a very high level and illustration of a chassis and a blade. So we have, for a CPU partition, you have 2 nodes cards and 2 nodes on each card. For the GPU partition, you will have each blade has 2 nodes because they have to leave space for the 4 GPUs on each node for the GPU nodes. A compute processor. So on the CPU side, we have what we call a Zen 3 CPU, or the code name Milan. So this is an AMD GPU. Both Cetonix is powered by AMD GPUs and CPUs, which is a relatively new vendor in the space of supercomputing, where previously was dominated by Intel, and we had NVIDIA's for GPUs in other systems. Now AMD is making its way to the space of supercomputing and high-performance computing. In our case, we have a Zen 3 architecture on the CPU side, which each node or each CPU has 64 cores. 64 cores are grouped in groups of 8 cores. Each group make a compute die. What we call Zen compute die. So I don't remember the whole name, Chris, if you remember that. But it's basically a single chip. It contains 8 cores, and they all share the L3 cache, the single L3 cache. So you have 8 groups of 8 CPU cores, and each group shares an L3 cache, which is of the size 32 megabytes. Then each core itself has an L1, L2 cache for data and instructions. Now, what I want to point out that is that in the previous systems might have had less cores. For instance, our previous supercomputer had only 24 cores on a CPU, and they all share the same L3 cache. Now, in this case, because we have many more cores, we have different L3 cache, one for each group of 8 cores. In some way, the L3 cache is partitioned across cores, and that has some implications in terms of performance in the way you place your computation on this course. And this is covered also in other slides later on. All the cores, though, will have access to the memory chiplet that then will give it access to the various RAM module or memory modules available for the entire node. So each core can access the memory, but depending on which core and which memory you access, it can take slightly longer or shorter, depending on the access pattern, essentially. So it's a complex system of CPUs and memory that needs to be taken into account when you place your computation on them. On the GPU side, each GPU blade has 2 GPU nodes, and you can see here, and as you can see also in the blades that we have in exposure here, we have 4 GPUs for each node. Each GPU is a MI250X, which is an AMD GPU. It has a total 120 gigabytes of memory and around 220 compute units, which are the equivalent of streaming multiprocessors on the AMD on the NVIDIA GPUs. But actually, each AMD MI250X GPU is made of 2 GCDs, or graphics compute dies. It means that the memory and the compute units are partitioned equally on 2 different dies. And as far as the supercomputer is concerned, these are considered 2 distinct GPUs. So they are physically very close together and coupled together, but on the logical level, they are seen from the software as 2 separate GPUs. So on a physical level, a GPU node has 4 GPUs, but on the software side, you will see them as 8 GPUs. We can call them GCDs or virtual GPUs or SLAM GPUs, depending on the practical level. Essentially, the software will see 8 GPUs. Okay, so we are towards the end of this first slide deck, and what we have covered is the terms of petaflop. So how do we measure the performance of a supercomputer? What are the key components of a supercomputer? We covered the login nodes, compute nodes, scheduler, and etc. And hopefully you have a clearer idea on how supercomputer allow computations to be performed faster on a bigger scale. As I said, we have a documentation you can access throughout the internship. It's always accessible to the public, and it contains all the information I covered now and all the information that will be covered later. Any questions so far? Okay. So the next module